Good evening, everyone. I am Anish Ambekar, PMRF and PhD candidate from Aerospace Engineering IIC Bengaluru. Welcome to the live interaction session for NPTEL course Solid Mechanics. This course is being offered by Professor Ajit Kumar of IIT Delhi. In this week, we'll cover some problems related to the concepts taught in the week 9. These include bending of symmetrical as well as unsymmetrical beams, both pure bending as well as non-uniform bending. We have also Professor Ajit also covered uh, thin beams with thin cross sections as well. Okay, we'll move to the first problem. The first problem asks: consider a beam with its axis along unit vector E1. Which of the following will lead to the bending of the beam? So we have a beam like this. Its length is along E1, its axis is along E1. E1, we have E2 and E3, and we are asked which of the scenarios would lead to bending of the beam. So okay, the first case is moment along E1. So if you have a moment along E1, it would act something like this, right? This moment along E1 would cause a twisting of the beam, correct? Next, so this would cause twisting of the beam. The second option is moment along E2. So this is your moment along E2. If we apply this load, our beam will curve in this direction, like this. So this will cause a bending of beam. So this will cause bending, and the beam would basically be curved in the E2 E1 plane. The third option is moment along E3. So you would have something like this. This is the moment along E3. In this case, the beam would, so it's difficult to show this, but the beam would, for the M2 case, the beam would be curving. For the M2 case, the beam will be curving along E3 E1 plane, whereas for the if M3, which is the moment applied along E3, then the beam will curve in the E2 E1 plane. Yeah. So option B and C would give us bending of the beam. Note that here I have assumed this beam, or rather drawn the beam to be symmetrical, but this doesn't need to be the case. You can have a beam with a asymmetrical cross section and you would still have bending if moments are applied along E2 and E3 direction. Next up, problem number 2. It's a simple true or false statement. We are asked to judge the statement. In the analysis of pure bending of a beam whose axis is along x-axis, sigma yy and sigma zz are taken to be 0 throughout the beam. This is done because the beam is allowed to relax freely in the y and z directions. So is this true? Do you know if this is true? This is your beam x, y and z, and this is the geometry, and we are asked about sigma yy and sigma zz throughout the beam. So if the beam is undergoing pure bending, so you could have something like an mz load, or equivalently you could have my loads as well, equivalent opposite my loads, and they would cause pure bending of this beam. In such a case, there are no other tractions acting on any of the surfaces apart from, say, the N2 surfaces. And in this case, the beam can freely move along y and z direction till it reaches its equilibrium point, or equilibrium state rather. So in that case, you have no loads acting either along y or along z axis, and therefore we can take this assumption like it's a therefore we can take this sigma yy and sigma zz to be 0 while analyzing this beam. Okay,
True.
so this is statement is true.
True. True.
Next up is problem number 3. Consider two geometrically identical beams made of different materials with their axis along x-axis. Young's modulus for the two materials are different. Identical terminal couples along z-axis are applied at the two ends of the two beams. And which of the following statements is true? So we are asked to consider two identical beams with axis along x-axis. So suppose this is beam 1 and suppose this is beam 2. And I'll just draw a coordinate frame here for reference: x, y, and z. And you have an identical couple. So I'm just directly drawing the torque being produced by the couple applied at the ends. I'll name this as 1 for beam 1 and 2 for beam 2. And we know that material 1 is not equal to material of beam 2. And then we are asked either about the sigma xx and epsilon xx. Okay, so if you remember, epsilon xx is nothing but minus y by r, correct? And sigma xx ey by r. Upon simplifying, we know that if we write kappa, which is the curvature, is 1 by r, then we know the relation between applied load is applied moment is equal to bending stiffness into curvature. Therefore, we can rewrite epsilon xx is equal to minus y kappa and sigma xx to be minus ey kappa. But we know that E into kappa is nothing but m by mz by izz. So this is what we end up with: minus y mz by eizz. So these are the two equations for sigma xx and epsilon xx. Since the two beams are identical, we geometrically identical, we know that izz for beam 1 should be equal to izz for beam 2, correct? And also mz is same. Therefore, I'll just name this as equation 1. Therefore, using equation 1, what we obtain is sigma xx of beam 1 should be equal to sigma xx of beam 2. Correct? So variation of sigma xx in the two beams is identical, which is the first option. Similarly, if we use 2, what we get is epsilon xx of 1 upon epsilon xx of 2 should be equal to E2 by E1. Is this correct? Which is not equal to 1. Therefore, variation of epsilon xx in the two beams should be different. So we end up with options A and D. Next up, we have problem number 4. Consider pure bending of a rectangular beam whose axis is along the x-axis. Moment is applied along the z-axis. Which of the following is or are true regarding the cross section of the beam? So we have a beam whose axis is along the x-axis. This is our beam. This is our coordinate frame x, y, and z. And we are told that this is under pure bending with moment applied along z axis. So you have got mz acting on both the leftmost and the rightmost ends. And let us go through all the statements one by one. So statement 1 is lines parallel to z axis in the undeformed cross section get curved after deformation. So if you remember, we'll go through it like this. Epsilon xx is nothing but minus y by r. Epsilon yy becomes nu y by r. Epsilon zz becomes nu y by r. Okay, and so nu is the Poisson ratio. We assume isotropic beam, isotropic material making up the beam. So we have only one Poisson ratio. And using this, what we can see is that if I draw this as the beam cross section, I label this point O as the center of the beam, and the beam is given as rectangular. So this is the height h, this is the depth or width b, and I'll label the four corners as A, B, C, D. Now if I draw a line, EF, which is parallel to y-axis, we can see that for EF there is epsilon yy is, so for EF parallel to y-axis, we can see that epsilon yy is greater than 0 for y greater than 0, and epsilon yy is less than 0 for y less than 0. We can integrate epsilon yy to figure out displacement uy between points E and F, and we see that the length of EF remains unchanged. Therefore, the easiest way to go about this is simply to integrate Eyy into dy. That should give you change in length of EF. That change in length of EF comes out to be 0. And therefore, if you take a line parallel to y-axis in the undeformed cross section, it remains the same. Okay. What are we asked? Lines parallel to what options are we in? Lines parallel to y-axis in the undeformed cross section get curved after deformation. No, they don't get curved. Right? They remain unchanged. Similarly, if we look at a different line, say GH, if we look at a line GH which is parallel to z-axis in undeformed configuration, you see that epsilon zz is greater than 0 for epsilon zz if GH lies above origin, lies above the centroid, and epsilon zz is less than 0 if GH lies below centroid. Therefore, you will have, this is nothing but elongation and this is compression. So lines above the z-axis would be elongated, lines parallel to the z-axis and below the centroid would be compressed. But if we do a simple analysis, it would seem like these are the lines that are occurring. But if the net shape ends up becoming if the shape ends up becoming like a trapezoid, then you can see that this angle is not equal to pi by 2, which should tell you that some shear strain and shear stress are generated. But that is not the case, because we know that this surface has to be traction free. Therefore, this angle needs to be 90°, but this line needs to elongate. So what we end up with is cross section, which is so what we end up with is a curved sort of cross section. So we end up with a curved cross section. So we end up with something like this. So the lines above are elongated, lines below are compressed, but when they meet the free surface, they are always perpendicular to each other. So lines parallel to z-axis get curved after deformation. Okay. Next up, we have problem number 5. Again, this is a true or false statement. The statement that is given is as follows. The equation m equal to ei kappa is valid for non-uniform bending or symmetrical beams. Here m is the applied moment, ei is the bending modulus, and kappa is the curvature. So is this statement true or false? Do you know? So in general, you can have even for non-uniform. So since we have symmetrical beams, your eye would be fixed, and if you have a same material again, your E is also fixed. But in general, this equation can hold true even if there is a variation in the bending moment along the length of the beam. So this equation in general is true even in the case of a non-uniform bend. Problem number 6. Consider an I-beam with its axis along the x-axis clamped at one end. A uniformly distributed load is applied on the top face of the beam along the y-axis. If we plot the shear stress tau xy versus y plot for the cross section of the beam, what would it look like? So I'll just draw this beam. Draw it like this. So these are these two internal lines form the stem. So your beam would look something, cross section would look something like this. This is your I beam, and this is your coordinate x, y, and z, and it's clamped at the left end, and you have a uniformly distributed load. I'll choose a different ink once. We have a uniformly distributed load acting like this. Okay, this is our uniformly distributed load. B of x is equal to b, and we are asked to comment on the nature of tau xy. So if we plot tau, if I show this will be tau yx. So we are asked to comment on tau x as a function of y. Okay. So we have a few relations. So first of all, rate of change of, so rate of change of shear along the, these are pointed, I'm showing that these are all pointed downwards, and I'm looking at a particular cross section at a distance x. If I look at that cross section, then I would have something like v of x plus delta x. I'll have a b load acting here, b of x, and this is v of x, and I'll also have moments. But if I just do a force balance along the y-axis, what I find is dv by dx minus b of x is 0. Therefore, dv by dx is equal to b of x, which is nothing but b. And from this I can figure out my v to be something of the form bx plus some constant c1, right? This constant c1 we can find by looking at, say, either the left or the right, and you can see that on the left hand, this left face, this traction, rightmost face is traction free, and therefore your shear should vanish there. You can just plug into that to figure out c. Similarly, if I look at the moment, then we have dm by dx plus v of x is 0, which should give you as mz, I just said vy of x, mz of x to be of the form b by 2 minus b by 2 x square minus c1x plus c2. Something like this would be your m plot. So we are interested in tau xy, so we look only at v of y. If we fix x and we call, if we fix x, then we'll just call our vy of x to be some value v, and you'll have your tau xy acting here, and the overall summation of your tau xy multiplied by the area should be equal to v. Okay, so if we fix some x, your v becomes fixed, and then you can proceed to we actually have to take one more assumption where we say that our tau xy is rather independent of z. Once you take that, all your shears for a particular z would carry the same value. And once you go through the whole integration process, your tau xy at a point x comma y turns out to be q of x q of y upon izz into, okay, I need to differentiate. I'll write this as w of y. So w of y wz of y refers to this width. Wz of y would refer to this width. So this can be wz at particular y. This can be wz at another y. We can see that in this equation, since we fix x, your v would be fixed. Your izz would also be fixed because it accounts for the entire area. Your q of y would be nothing but whatever point you choose on the. So I'll take 2 points on the IB. Suppose I choose this as y1 and another one as y2. So your q of y would be nothing but y centroid into area, and similarly for y2 it would be some another y centroid dash into area dash. So your q centroid would vary, and similarly your w would vary. Once we come from top to this point, which is say y is equal to y0, you would see that your q of y is a quadratic function, and therefore therefore would steadily increase as we go. Therefore your tau xy would quadratically increase with y as we go down, but then suddenly you have a jump and your width along y, wz of y2 is much less than wz of y1, in which case your tau xy would suddenly jump ahead, and therefore your overall plot should look something like this. This is y is equal to y naught, which is the point where your cross section is changing, and these are the two end points. So you would have something like this, quick sharp change, then again till y equal to minus 2, again a sharp change going to 0 on the free ends. So this is how your overall plot should look like. So option C is the one I think that best describes this, that you have a jump in the value of tau xy at points where the width of the cross section, so just nothing but wz of y, changes. Problem number 7. Again, this is a simple true or false statement. We consider a cylindrical beam with its axis along the x-axis clamped at one end. So we have a cylindrical beam like this, and we are clamping, say, the left end. A uniformly distributed load is applied on the top face of the beam along the x-axis. Sorry, along the y-axis. I draw a coordinate frame y, x, and z. This is the, say, uniform load b of x is equal to v, and for such a beam we are asked tau xy, if tau xy is uniform at every point y equal to c on the cross section. So if I draw the cross section, it would look something like this. You have a y, you have your y-axis, you have your z-axis, you have your centroid of the beam. Suppose tau xy is uniform for every y equal to c. So if I fix some y value, then my entire tau xy would be fixed to one particular value. If that is the case, you can see that right near the edges, right near the end points, you have a your shear stress is basically such that it has a normal, you can like split it into a normal and a tangential component whose normal part is non-zero, but we know that your sorry but we know that, suppose you, I think taking the bottom half would be a better idea. Suppose I take the bottom half and I look at the shear values, and if they are all of the same magnitude, you can see that right at the periphery points, which are say point C and D, you would have a non-zero traction coming normal to your outer surface, which would imply that your, like, this point C and D are under some external load, under some external traction, which is clearly not the case, because we know that even if there is a load acting on the top half, there is no load acting on the bottom half. And if we take tau xy to be uniform at every point y equal to c, we should, this relation should also hold for the bottom half, and for the bottom half we know that the external surfaces are traction free. Choosing this particular form of tau xy, or rather putting this restriction on tau xy, would essentially violate the free traction surface boundary condition of the lower half. Thus, this particular statement is false. This is, I hope this is clear. We'll move on to problem number 8. Consider bending of a beam having unsymmetrical cross section. So, and the axis of the beam is aligned along the x-axis, and bending moment is applied along the y-axis. Okay, so we are told that my is applied. I take, suppose this as my beam cross section, draw it along x-axis. This is an unsymmetrical cross section, and it, you can see that this cross section is unsymmetrical, and therefore they are satisfying the given condition. and drawing a coordinate frame x, y, and z. Okay, and the bending moment is applied along y. So you have got my, which is being applied, and we are given values of iyz and izz, and we are asked what angle does the neutral axis make with the y-axis. So if you look at the general case of an unsymmetrical cross section with say y and z axis, and this so this is, suppose beta is the angle that your neutral axis, I'm sorry, just a second. Sorry. Yeah. This is we take neutral axis. So neutral axis we know will still pass through the centroid, and it would now make an angle beta with the y-axis. And we are asked about the. We are essentially asked to calculate the angle beta. We know that in this particular case, and if we calculate the moment about the centroid O, it is nothing but it's of the form y k hat plus z k hat cross sigma xx I dA. If I go through the integration process and figure it out exactly, I essentially have MO to be made up of moment along y-axis and moment along z-axis, where moment along y-axis is nothing but e kappa Iyy cos beta minus Iyz sin beta, and moment along z-axis to be equal to e kappa Izz sin beta minus Iyz cos beta. We are told that my is non-zero, but my is non-zero and it is the applied load. Therefore, mz, since mz is not applied, mz we can take 0. And if we look at this equation, in general, obviously E is non-zero, kappa also can be non-zero. Therefore, this equation Izz sin beta minus Iyy cos beta should be equal to 0. We know that Izz is 2, so Izz sin beta minus Iyy cos beta should be equal to 0. If I just rewrite this, my tan beta would be equal to Iyy by Izz, sorry, Iyz by Izz, which is nothing but, sorry, 2 by 2 root 3. Yeah, 2 by 2 root 3, which is 1 by root 3. Therefore, my beta would be tan inverse of 1 by root 3, which we know to be equal to 30 degrees. So 30 degrees is the angle that the neutral axis makes with the y-axis. Problem number 9. Consider, problem number 9 is again a true or false statement. The statement which is given is as follows. Consider an unsymmetrical beam Equal and opposite moments are applied at the ends of the beam in a direction perpendicular to the axis of the beam. In such case, bending moment is constant along the axis of the beam and no shear stresses, and there is no shear stresses in the beam. So I'll again draw a general unsymmetrical cross section. I'll choose a coordinate frame, say x, y and z, and a general moment would be m is equal to my j hat plus mz k hat, and on the other hand we would have a plus m and minus m acting. Okay, these are your two bending moments, and in such a case there is no shear stress in the beam. So is this true or false? Do you know? Okay, the easiest way to go about this is, rather than thinking it of as my j hat plus mz k hat, suppose we just rewrite this to be some y1 and z1 axis, and your moment is essentially say applied along the y1 axis. So what you would have is m dash. M dash is the moment acts along y dash axis. Since your moment is arbitrary, we can figure out this m dash, and if we then do a analysis of a small cross section, even if it's asymmetric, you can figure out that the applied moments would still be m dash. Because of force balance, you can figure out that at any point x equal to x, your applied moment should still be equal to m dash j hat. And if you look at our equation, dm by dx plus v of x. Sorry, I'll take this along z axis to simplify. Then we'll have directly this result. And we know that m dash is acting along k dash, which is the direction unit vector along z dash axis. And then we have this equation for force, for the force balance, coming from the moment balance. So this comes from, I can write it as from torque balance to simplify things. Now I know that my mz is equal to m dash is constant. Therefore my dmz by dx becomes 0, which means that my vy is 0. So there is no shear load, there is no shear stress acting along the face of the beam, along the cross section of the beam. Okay, so no shear stresses are generated. Got it? Okay. Problem number 10. Consider non-uniform bending of a beam whose axis is along x-axis. So this is our beam. Its axis is along x-axis. And we are given moment mz of x is equal to 3x plus 2 Newton meter, and moment my of x is equal to 6x plus 5 Newton meter. And we are asked to calculate shear forces Vy and Vz. So if you apply moment balance, if you apply torque balance along z, what you end up with is dmz by dx plus Vy is equal to 0, which implies that Vy should be equal to minus dmz by dx, which is nothing but minus 3. Similarly, if you now apply torque balance, or rather it should be angular momentum, so equilibrium along y-axis rather, what you would get is dmy by dx minus vz. In this case you get a minus sign. You can work this out as well. So your Vz becomes nothing but plus dmy by dx. This is 6. Okay, so which are the options?
Last one.
Last one is Vz, and Vy is this one. Yeah, Vy is minus. Correct. So these are the two options. Vy is minus 3 Newton and Vz is 6 Newton. Okay, that covers up the example problems I had. Do you have any other doubts?
No, sir, no, it's a very nice session, sir.
Okay, thank you. Uh, in that case, thank you for attending this class or viewing it on the YouTube. We'll meet again at the same time. So next Tuesday at the same time from 7 to 8 p.m. to discuss week 10 content.
Okay.
Thank you.